Yeah, good morning, my dear students. I am going to discuss the topic on mathematical parameters involved in chromatography. So, these are the very important basic techniques used in chromatography for separations. So, what are all the mathematical parameters? Before going to discuss about the mathematical parameters, we will first discuss about the chromatogram. What is called a chromatogram? Chromatogram is basically a graph obtained in chromatography. If you are capable to do the gas liquid chromatography or high performance liquid chromatography, finally you are getting the peak, right? The graph whatever you are getting is called as chromatogram. Just for example, I have just shown the plot here between the time versus detector response. I am just plotting the elution time versus the detector response in chromatography. And here this is an example of gas liquid chromatography where I am injecting the sample here. After injecting the sample here, the methane is a mobile phase of the gas chromatography. So the mobile phase is giving the peak here. Then after that the octane is giving a peak here. Then the unknown sample is giving a specific peak over here. Then nonane is giving another peak here. Now what is called a chromatogram? Chromatogram is basically a graph showing the detector response as a function of elution time. Showing the detector response as a function of elution time. So that is called chromatogram. The second important aspect, mathematical parameter involved in chromatography is called retention time. Retention time is given by the technical term that is called TR, right? So what is called retention time? The retention time is the time needed after injection of the mixture onto the column until that component reaches the detector. So I am injecting the sample will be going into the column and finally reaching the detector. So that is called retention time, right? So in other words, we can say the time required to elute 50% of component from the column. That means I am injecting here and here the unknown sample 50%. This is the 50% of the unknown sample. You can see here. This is the unknown sample, 50% of the unknown sample. The time after injection, it is going into the column and reaching the detector. Finally, I am getting 50% of the components will be eluted. So this time is called retention time, which is also called as TR, right? Now, what is called retention volume? The third important parameter is retention volume. We also call it as VR. So basically, retention volume can be calculated if you know the retention time. If you multiply the retention time with the flow rate of the mobile phase, then you will get the retention volume, right? So what is called retention volume? It is the volume of the mobile phase required to elute 50% of component from the column. How much amount of or how much volume of the mobile phase we are using to elute 50% of the component from the column, unknown component from the column. That is called as retention volume. So VR is equal to TR into UV. What is called UV? This is nothing but volume flow rate of the mobile phase, right? The fourth important parameter is adjusted retention time. The adjusted retention time is also given by TR dash. What is called adjusted retention time? Basically, you should remember one important thing. So when I inject the sample, I am getting 50% of the component from the column. So this is called TR. After injecting the sample, I am getting 50% of the component from the column. This is called TR. It is the retention time, right? Now, what we can say this, the mobile phase, initially after injecting the sample, the mobile phase itself will be giving a peak here. The mobile phase, that means we can say the saturation. Initially, the mobile phase itself will be giving a peak, right? So that peak from the point of injection where we are getting the mobile phase peak, the carrier gas in gas chromatography, methane is giving a peak here. So that distance is called as Tm, right? So if you subtract the TR, right? If you subtract the TR minus Tm, then you will be getting TR dash. It is called as adjusted retention time, right? I will show that. What is adjusted retention time? It is the additional time required for the solute to travel the length of the column beyond the time required by the unretained solvent. So it is basically the additional time required for the solute to travel the length of the column beyond the time required by the unretained solvent. So initially the solvent is giving a peak. After that point, how much time it is, additional time it is required by the sample to finally giving the peak here. So that is called adjusted retention time. So adjusted retention time means we have to subtract the mobile phase from the original retention time. The mobile phase time from the original retention time. Where the mobile phase is giving a peak, from there we have to subtract from the original retention time. That is called adjusted retention time. Right? So that is the simply we can say the additional time required for the solute, right? Required for the solute to travel the length of the column beyond the time required by the unretained solvent, right? Which is not retained. Therefore, the solvent is giving a peak here, right? So TR dash is equal to TR minus TM. What is called TM? It is the unretained mobile phase travels through the column in a minimum possible time. In a very short time interval, you will be getting this unretained mobile phase, that is called as TM. Where the point of injection and where the methane is giving a peak, that point from this terminal is called TM. Unretained mobile phase travels through the column in a very minimum possible time. Right? Particularly in case of gas chromatography, this retention, this TM is the time needed for methane to travel through the length of the column. Right? So this is the fourth important parameter. Now coming to the fifth parameter, we call them as relative retention. What is the meaning of relative retention? It is also called as alpha. Right? So relative retention means we have to compare between two components. For any two components 1 and 2, the relative retention is the ratio of their adjusted retention times. So I am taking alpha relative retention is equal to adjusted retention time of the second component divided by adjusted retention time of the first component. So TR dash for the second component divided by TR dash for the first component. So the second component adjusted retention time will be greater than the first component adjusted retention time. So therefore alpha is also greater than 1. So what is the observation from this relative retention? So greater the relative retention value, greater the separation between two components. So if you have two components and they are giving two different peaks, if you have the relative retention, that is alpha value is greater, so you can simply say that the separation between the two components will be better, right? So greater the relative retention, greater the separation between two components. Now coming to the sixth important mathematical parameter called capacity factor. The capacity factor is given by the terminology K dash. For each peak, whatever you are getting in the chromatogram, this is a chromatogram between the elution time versus detector response. So each peak, here one peak, here one peak, here one peak, here one peak you are getting, right? So for each peak in the chromatogram, K dash capacity factor is equal to TR minus TM divided by TM. What is TR minus TM? It is the adjusted retention time. So when you just put adjusted retention time in the numerator, and in the denominator if you put TM, that is the unretained mobile phase travels through the column in a minimum possible time. So that ratio we call them as capacity factor or called as K dash, right? So longer the component retained by the column, the greater the capacity factor. If any component is retained by the column for longer time period, automatically the capacity factor will be very, very high. So in other words, K dash is equal to CS into Vs divided by Cm into Vm. What is CS? Concentration of solute in the stationary phase, that is called CS, and Vs is the volume of the stationary phase, right? So CS is the concentration of the solute in stationary phase and Vs is the volume of the stationary phase and vice versa. So but K is equal to, but generally K is called as partition coefficient, that is equal to CS divided by Cm. What is CS? Concentration of the solute in the stationary phase by concentration of solute in the mobile phase. Partition coefficient or distribution coefficient between two different phases. So K dash is equal to K into Vs by Vm, or in other words we can say that TR minus Tm divided by Tm, or adjusted retention time TR dash divided by Tm, right? So in this case relative retention alpha can be given as the adjusted retention time of the second component divided by adjusted retention time of the first component, or simply we can say that K dash capacity factor of the second component divided by capacity factor of the first component, right? So the relative retention of the two solutes is proportional to the ratio of their partition coefficients. We can come to the conclusion. the relative retention of two solutes is proportional to the ratio of their partition coefficients. And this is the physical basis of chromatography and its separation. The next important terminology what we are using is resolution. Resolution is also a terminology which is used to compare the two peaks. Which peak is having better resolution, right? So resolution of the two peaks from each other is given by the formula R is equal to delta TR divided by width average, WAV. Delta TR is also equivalent to delta VR divided by width average. So what is delta TR? Delta TR you know very well. If you have two peaks, that means one peak is having 5 minutes as the retention time, another peak is having 10 minutes as the retention time. So the difference between these two retention time, that is called delta TR. So 10 minus 5 is equal to 5 minutes, right? So delta TR is the separation between the two peaks, and the width average, WAV, is the average width of the two peaks. How much is the width of the two peaks, right? The average width of the two peaks. That means the width of the first peak plus width of the second peak divided by 2. So the average width of the two peaks is called WAV, right? Then the another important factor we are going to discuss is diffusion. Diffusion is the main cause of band spreading. As I already told, in chromatography, we are getting the bands or zones getting separated when you are going to separate different components from the mixture, right? So this diffusion is one of the very important cause of band spreading, and diffusion coefficient measures the rate at which a substance moves randomly from a region of higher concentration to lower concentration. Whenever we talk about the diffusion from higher concentration to lower concentration, so what is happening? Diffusion coefficient measures the rate at which a substance or molecule moves randomly from a higher concentration to lower concentration. So diffusion is given by the formula J is equal to minus D into dC by dx, where J is nothing but the flux of the molecule diffusing across a plane of unit area in a particular area, right? What is the flux of the molecules diffusing across a plane of a specific unit area? That is called J value. This law is called fixed law of diffusion, and D is the diffusion coefficient, as we already discussed, and this dC by dx is the concentration gradient. So this is all about the various mathematical parameters for chromatography, especially the physical basis or the basic equations describing the chromatographic separations, right? So I think some more parameters are also there that we will discuss in the further classes. Thank you very much. Thank you, my dear students.